Hello students, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Satendra Vats, Assistant Professor in ETCE Department. Our today's topic is different types of noise in communication systems, which is a part of Unit 1st of Subject Communication Systems in ETCE 4th semester. Okay. So let's start. What is noise? Noise can be defined in electrical terms as an unwanted signal or unwanted introduction of energy, that is electrical energy, that tends to interfere with the proper reception and reproduction of transmitted signals at the receiver end. So because as we can see, the noise is an unwanted signal which can get mixed with the original signal and may affect the reception at the receiver end. So we may not get the original function which was transmitted from the transmitter, and we may get a different signal at the receiving end which may not be having the complete information as it was transmitted from the transmitter. For example, in radio receivers, noise may produce hiss sound in the loudspeaker output, or in television receivers, the noise can come in form of confetti or snow-like noise on the picture screen, which you may have noticed also. Like in our radio receivers, sometimes with the voice signal we get the noise of hiss kind of sound sometimes received on the radio receivers with the voice signals. Okay, in pulse communication systems, noise may produce unwanted pulses or perhaps cancels out the wanted ones. So let's say if we have this sort of pulse that was transmitted, if some unwanted pulse or some signal is mixed with this signal, it may result in, like if it was 1 here 0 here 1 here 0 here, so it can affect our original signal. So instead of 1 we may get 0, or instead of 0 we may get 1. So the information will be completely changed and we will get a false signal at the receiver. Okay, so noise can affect our communication system in various ways. It can limit the range of systems for a given transmitted power. That is, if we were using the receiver for a frequency range of f1 to f2, the noise can affect this frequency range. We may not get the signals within this range, or we may get a signal outside of this range as well. So it affects the range of the systems. Secondly, it can affect the sensitivity of the receivers also. Okay, so it can limit the sensitivity. And what is sensitivity of a receiver? Sensitivity is the ability of any receiver to receive the weakest of the signals, that is how much small frequency signal it can amplify, or how much small amplitude of a signal it can amplify. So if noise comes in between the transmission channel, it may affect the sensitivity of the receiver. It may now not amplify the signals which it was amplifying before. Okay, so classification of noise is broadly based into two categories, that is external noise and internal noise. So external noises are the noises which comes from outside of the system. That is the source of the noises. This is our system. The source of the noise in case of external noise is outside of our system, and internal noise can be seen as the noise generated within this system. That is because of the equipments or the circuitry used in our communication system. So external noise can also be classified as atmospheric noise. That is the source of the noise which is in our atmosphere, Earth's atmosphere. If the source of the noise is within our Earth's atmosphere, then it will be categorized as atmospheric noise. So atmospheric noise consists of spurious radio signals, that is duplicated radio signals, which are just like the real radio signals but are not real radio signals. Okay, so their properties may look like the real radio spectrum, but they are not the actual radio signals. So these components of this atmospheric noise is distributed over a wide range of frequencies, so it can affect a lot of our amplifiers and receivers. Okay, so this external noise or the atmospheric noise is propagated over the earth in the same way as ordinary radio signals. Like we have seen that the radio signals, if this is the ionosphere, radio signals get back from reflected after this ionosphere. So in the same way, these atmospheric noise can get back reflected from the ionosphere and travels as the radio signals and can get mixed with our radio signals, which can affect our original signal at the receiver end. Okay, so the strength of these atmospheric noises is inversely proportional to the frequency. So their strength is inversely proportional to frequency, means at higher frequencies the effect of external noise keeps on decreasing. If the frequency is increased, the effect of atmospheric noise is decreased. Okay, so atmospheric noise becomes less severe at a frequency above 30 megahertz. As I have said, the effect of this atmospheric noise is less at higher frequencies, that is above 13 megahertz. It will not have much of effect. Then comes extraterrestrial noise, that is the noises which have sources outside of our Earth's atmosphere. This is also called space noises, as the source of these noises outside our Earth's atmosphere. So first is solar noise. Under the normal conditions, there is a constant noise radiation from the sun, as the temperature of the sun is quite large, that is in the range of 6000 degree Celsius. So at this much of higher temperature, it is quite natural for a body to radiate energy. So since the temperature is much higher in the sun, it radiates regular energy, and it radiates over a very broad frequency spectrum, which includes the frequency we use for our communication systems. So sun radiates continuous energy at a broad frequency spectrum that we also use in our communication system. So it is natural that it will affect our communication system at the receiver end. So next is cosmic noise. It is caused by the distant stars, as the stars are also the suns, or we can say sun is also a star. So These stars also have very high temperatures, but they are very distant from the earth as compared to the sun. But when we combine all the stars, there will be a considerable amount of RF noise created in the space that can affect our communication systems. But this cosmic noise is also inversely proportional to the frequency, so it will affect only the systems working in this range, that is 8 megahertz to 1.43 gigahertz. So at higher frequencies, that is greater than 2 gigahertz, it will not have that much of effect. So these noise are also called thermal or black body noises and distributed fairly uniformly over the entire sky. That is, the strength or the intensity of this cosmic noise is more or less uniform in the entire Earth's atmosphere. So it will affect some communication system in India in the same manner as it will affect it in the America. So it will have the same effect as it is uniformly distributed over the entire atmosphere. So next is industrial noise. It includes noise in the frequency of 1 to 600 megahertz. Okay, it includes the frequency range of 1 to 600 megahertz, and it comes from like the automobiles, aircrafts, trains, electric motors, leakages from the high tension wires, or from heavy electrical machines. So that is why we place our satellite earth stations and radio telescopes away from the city noises in the quiet place like some valley or in mountains, because to avoid these industrial noises. Okay, then we come to internal noise. That is, if the source of the noise is within the system, within the communication system, that then it will be called the internal noise. So first is thermal agitation noise, which is generated by the resistive part of the circuitry. Every circuit, every amplifier or a mixture has some resistive component in it, so it will generate the thermal agitation noise, which is also called the white noise or Johnson noise. So in your semester exams, it comes with the name Johnson noise or white noise. So it is one and the same thing. Okay, so it is due to the rapid and random motion of the molecules, or it is because of the kinetic energy of the atoms or electrons inside the resistive circuit. The noise generated by a resistor is directly proportional to the absolute temperature. Okay, it is directly proportional to the temperature and directly proportional to the bandwidth. So the power, that is the noise power generated in the resistive circuit, is directly proportional to the temperature multiplied by bandwidth. So here we can equate it and put a proportionality constant K, which is called Boltzmann constant and has a value of 1.38 into 10 raised to power minus 23 joules per Kelvin, where T is the absolute temperature and temperature will be taken in Kelvin scale, where delta F is the bandwidth of the interest, that is the bandwidth on which we are working on. So this is how we can calculate the noise power of a resistive part of the system. So equivalent circuit of the resistor which is generating the noise can be drawn as I have drawn here. Here Vn is the noise voltage, this is the internal resistance, and it is connected to a load resistance, that is the output resistance. From this resistor's equivalent noise voltage Vn can be calculated using the maximum power transfer theorem. As you all know, in the maximum power transfer theorem, maximum power is transferred to the load resistance RL from the RS when RS is equal to RL, and this power would be V square by 4 RL or RS, as both of are same at the maximum power. So this comes out to be Vn square upon 4R, and when we put the value of Pn, that is the noise power, which is equal to 4 kT delta Fr, we would get the value of noise voltage as under root 4 kT into bandwidth into resistance. So this is the final equation of the noise voltage from a resistive element. Okay, so this is how we can calculate the noise voltage, that is the thermal agitation noise voltage. Okay, now next comes the another noise, which is the short noise. So another noise in all amplifying devices and active devices is short noise. It is caused by the random variation in the arrival of electrons or holes at the output electrode of the amplifying device. Sometimes it comes in the university exams in the 2 marks question, write a short note on short noise. So this is the variation appear as a randomly varying noise current superimposed on the output. So for a diode, we can write the equation of this short noise as IN. IN is the short noise RMS current, and which is equal to under root 2 E IP into del F, where E is the charge of electron, which is 1.6 into 10 raised to power minus 19 coulomb, and del F is the bandwidth of the system, that is the bandwidth of interest, or IP is the direct diode current. So this is the equation we want to calculate short noise in an amplifier. Okay, then comes the transit time noise. So this is also a noise which is generated inside a transistor we are using as an amplifier. It is the time, if the time taken by an electron to travel from emitter to the collector of a transistor becomes significant to the period of signal being amplified. That is, if let us see, if we are using some signal having a time period t, that is the time to complete the one cycle is t. So if this t, the magnitude of this time period t is significantly equal to the time taken by the electron to travel from emitter to the collector, then there will be a noise generated in the frequencies in the upper VHF range, as we have seen the VHF range in the radio frequency spectrum in last lecture. So this is called the transit time effect. It increases proportionally with the frequency, that is, it is directly proportional to the frequency. If the frequency increases, then this transit time noises will also increase in a transistor. Okay, then one more type of noise is flicker noise, which is the noise generated at lower frequencies only. So at low audio frequencies, some of the noise called flicker, or it is also called the modulation noise, which is generated in the transistors at low frequencies. It is proportional to the emitter current IE, and inversely proportional to frequency. So at frequencies greater than 500 Hz, it is not of any significance. So it is generated or affect the systems when the system is working at low frequency range as such as 500 hertz to 500 hertz. Beyond 500 hertz, the flicker noise will not have much effect on our communication system. So these are the some of the types of noises we need to study in our course, which comes in our MDO semester examinations. So you can learn all these types of noises, external noises and internal noises. In the next lecture we will see how we can calculate the noise at the receiver input and at the receiver output. We will also see the signal to noise ratio and noise figures in the next lecture. So thank you very much for listening. This is it for the lecture.